So we start the session. In uh, earlier class we covered the what is spring and type of spring. So I will discuss the stress equation in spring. So this is a diagram of a spring. This is a uh, mean dia of the spring and coil dia, or this is a mean dia of the spring. If you open the spring, then spring look like this type of. This is a mean wire diameter, and this is whole diameter of the spring. So let's see the nomenclature of the force W acting at the end of the bracket induced torsional shear stress in the bar. The torsional moment is given by, as we know, the torque equals to force into radius, and radius equals to dia by 2. The torsional shear stress in the bar is given by this equation derived by using the torsion equation. So put the value of a torque in this equation and get the value of a shear stress is 8 WD divided by pi dq, where W is the load, D is mean diameter, and small d is a wire diameter. When the equivalent bar is bent in the form of a helical coil, there are additional stress on account of the following factors. There are some factors which we have to take into account. There is a direct or transverse shear stress in the spring wire. When bar is bent in the form of coil, the length of the inside fiber is less than the length of the outside fiber. This results in stress concentration at the inside fiber of the coil. So let's see the some stress distribution in a diameter. When only shear stress is acting, here is direct stress acting. In this, shear stress and direct stress both acting. To take into consideration the effect of a direct shear stress and stress concentration due to curvature effect, we assume the following two factors. One is direct shear stress, it means only shear stress acting on a body. Then it is 1 plus d by d, and spring index is d by capital D by small d. It can be written 1 plus 1 upon 2c. And Kc factor to account for the stress concentration due to the curvature effect. The combined effect of these two factors is given by K equals to Ks plus Kc, or Ks into Kc. There is another factor is a wall factor, and a wall derived the equation for resultant stress, which include torsional shear stress, direct shear stress, and stress concentration due to curvature. This equation is given by, this is C is a spring index, is C equals to capital dia over small dia. Small d means mean coil diameter divided by wire diameter. And come to the next equation is a deflection equation. This formula is derived by using the torsion equation. As we know that T by J equals to G theta divided by L. By rearranging the formula, we get the angle of twist in the form of this. As we know, the value of T is W into D by 2, and the value of L is pi dn, and J is polar moment of inertia. The value of polar moment in inertia is pi by 32 d to the power 4. After rearranging the value, we get the final 16 WD square and GD to the power 4. As we know, the deflection by using this geometry, this is a half of the dia and load acting downward. There is some angle here, and this by using this data we calculate the deflection, and after to put the value of a deflection in this equation we get the deflection. Is spring in series and parallel connection. Connection of a spring in series in parallel just opposite to the resistance, because in 12th standard we already know the how spring how resistance is arranged in a series or a parallel. Similarly, but just opposite in resistance, in spring, when we spring in a series, then add deflection for both, add the deflection, and spring constant deflection add, and this is a k, this is stiffness of the spring, and spring is arranged in this manner. Similarly, if connection is parallel, then deflection are the same and load are 2, but here the load equal and deflection different, and just here deflection are same but load are different, so the connection stiffness is by adding different. So thank you for watching this video.